introducing today to Alejandra Sanchez-Rios' PhD defense. Ale has her Bachelor of Science in Oceanography from the Universidad Autónoma de California, Baja California, in Ensenada. She came to us in July 2011, where she was immediately conscripted into a half-baked idea to go study the inner shelf off Agate Beach and Yaquina Head. So pretty much like the boundary between the surf zone and the inner shelf. This was mostly Jonathan's core idea, but we dragged Jonathan, myself, Alejandra, Byung Ho, and a poor summer REU student of Emily's. Oh, no, sorry. Oh, that was yours. We took them out in Scott Happel's 24-foot fishing boat on a fairly decent day, but still there must have been like swell from different directions because everybody was sick. Everyone except Ale. I watched Jonathan go over, hurl over the rail. I was like stuck, fixating on the horizon, and Ale was just doing everything, like anything that needed to go in and out of the water. It was Ale who was doing it. And then it wasn't until afterwards, that Alejandro told me, "Oh, I was sick. I didn't feel good. I was just still doing my work." And from there, I knew we had a winner. So. Since then, Ale's been an exceptional graduate student. She's gone on 5 large research cruises all over the world. She's been a major contributor on those cruises. She's also been chief scientist on the Oceanus for the very first oceanography boot camp cruise. Alejandra has also been a big contributor to our college and the universities. She served on the graduate student committee. She served on the search committee for our new dean. And she's been an officer in the Association of Latino American Students for several years, and among other things. So, so she'll be presenting her thesis work. It'll be a 45-minute or so presentation. As usual, you guys will ask questions during it. That's fine. And at the end, we'll have time for questions. And then we'll excuse the public audience, and we'll proceed with Alejandra's examination.
There's a couple of spaces on front. First of all, thank you so much for coming. It's such an honor. I'm so happy to be able to share with you all the work that I've done in pursuit of that PhD degree. And I'm really excited to be here in front of you today. And thanks for the introductions. The title of my dissertation is The Role of Submesoscale Features in Transporting Heat and Salt Across Ocean Fronts. And I hope the goal of the dissertation is to be able to express what do I mean by transport of heat and salt across ocean fronts, which ocean fronts, and what do I mean by submesoscale features. And this work that I've done with my advisor, Hugh Sherman. Before starting, I wanted to do just a little bit of a preview of what this presentation is going to look like. I have divided this in 4 sections. The first one is I'll give a brief introduction of what do I mean by ocean front, what do I mean by submesoscale features, why do we care for these structures, what are the objectives of the dissertation, which then I try to address with 2 studies. The first one is in the Gulf Stream, North Wall, and the second study is in a different region. It's in the South China Sea, where we see Croatia current intruding into it. In both, we observe small-scale features, and then we examined how the small features then create mixing. And lastly, I'll do a summary and conclusion of the main findings for each study. Guys, let's start. Okay, so first, what do I mean by ocean front? What I have here is a surface temperature data. I did this from a webpage called The State of the Ocean, which I like a lot. And you can select any date. Right now is April 2018. And so warm water will be in red. Cold water, it's in the blue and green colors. And I'm going to be using this palette of colors throughout the entire talk. And what I present here is the subtropical gyre. And this gyre is characteristic for an asymmetric current. And so we have a strong current in the western current boundary of it. And you can really see it with the sea surface temperature of a strong flow going into the east, and that's the Gulf Stream current. These currents are really important. They're called western boundary currents. So in the Atlantic, we have the Gulf Stream. In the Pacific, we have the North Pacific, we have another current that's the Sanchez-Rios current. And I look into these two main currents. They're important because they carry heat and salt from the tropical areas up to the poles. And what I mean by front is a focus in this region. We see that as they go and flow to the east and they encounter colder waters, they create this sharp boundary between the warm and the cold water. And that's where I'm focusing. For the Gulf Stream is in this region. For the Gulf Stream is going to be, for the Sanchez-Rios current is going to be in a different region of their path. And in frontal structures like this, we can see a great variety of structures, frontal structures. And they can be produced by mesoscale steering. They can be produced by shear, and also, for example, from some mesoscale stabilities. And I'll take a minute a little bit to define what I mean by mesoscale. The first thing that comes to mind is length scale. So we think about like small features like 10 kilometers long. But I wanted to also make a point that so mesoscale is also a dynamical definition. It's not just length scale. And I'll use here the definition from a paper from Thomas, Tandon, and Mahdi in 2013, where they used the Rossby number and the Richardson number to explain where do we see some mesoscale features. And that's when the ratio, it gets a magnitude of order of 1. If you look at the characteristic of the scale, so in other words, what this is saying is that it's not just the length scale that's important. We have to look at the stratification. We have to look at the depth of that surface layer. We have to look at the shear of the velocity that we're looking at, and also the where latitude, where are we in the world, so at the Coriolis parameter. And all of them together has to give you an order of magnitude of 1. Fronts are regions when this can happen when you have a localized strengthening of the front, so when you have larger, stronger gradients. I'm using this diagram from Capet et al. 2008. So here, imagine this is the front that I showed you in the satellite data. This is the warm water and the cold water. The lines here are isopignals. And you can see in front, they're upcrop. That means that something that was on deeper water is going down to the surface. And this is the heavy and the light side of the front. And so when you have a localized a region like this, and then you start intensifying the front, you are then bringing this ratio to 1. In other words, you're combining all these characteristics to create secondary circulations. So you're slowly progressing away from geostrophy balance. This secondary circulation is important in fronts because there's the ones that are responsible in transporting between the boundary, so between cold and warm water, and vertically. And the vertical velocities are also really important in this kind of locations for the exchange between the upper layer and the inner layer. This kind of circulation, again, that we're calling secondary circulations, are responsible for creating all sorts of structures at the fronts. So now I'm going to another part of the world. This is the South Ocean example, but it's also a strong front. This is data. This is not satellite data. This is actually data taken on the field by Taylor et al. 2018. We see that we have warm water, and then we have cold water, and this is the boundary between those two. And now we also have vertical data. And what we see is that what they did here is follow the surface of that 3 degrees Celsius. And we can see that there also are variability on the vertical. And we can see, for example, this structure here intruding into the warm water. By different authors, this kind of structures have been called shingles, tongues, streamers. They also create thermoline interleaving. And they can then create exchange between the 2 water masses, the cold and the warm water. And those are the kind of structures I'm interested in, and trying to understand how this small scale features are transferring between those 2 water masses. Why do we care for this? So I'm going to use now another diagram from Levy et al. 2012. So imagine this is X and Y, so this is like bird view. If you have patches of chlorophyll, and then you have, again, this localized region when you are squeezing those boundaries together, and you're kind of going to the regimen where you have the order of magnitude of 1. So we're going to the sub-mesoscale dynamics. And you generate, so now this is vertical, and this is the surface, and you generate the secondary circulation that we're talking about. The green is then phytoplankton and chlorophyll, and what we have here in purple is nutrients. The blue line here is the euphotic zone, which says how deep that light will penetrate in the water. So those secondary circulation help and inject the nutrients into that zone, the euphotic zone. And also you can have an injection of chlorophyll into the inner ocean. And then this will help support, for example, at the bottom bloom, that when that happens, you can then sustain order food chains are along the food chain. And you can see this in real data. So now what I'm showing you here is salinity and chlorophyll. So this is now depth, and this is along the track of a glider. This is a data from a work done by Beatriz et al. 2013. What we see here, so we have the high salinity surface, but we see patches of it being injected below. And you can trace that to also in chlorophyll. So this is kind of the example we're looking at, where we're like transporting laterally the chlorophyll and also into the inner ocean. So this kind of processes and dynamics are really important for enabling transport of tracers, in this case, for example, salinity and chlorophyll, and I focus on salinity and temperature. And enable that vertical and horizontal mixing across the fronts. And this is really important, for example, when you then have this mixing between two different water masses, in the creation of different type of water, for example, the formation of mode water. As an example, in the Atlantic of 18-degree mode water. But also in the advection of traces, as we mentioned. Parameterizing this mixing across those boundaries are really important for the use of them in ocean matters models and also climate models. And I'm focused on trying to understand then how that mixing occurs throughout those small scale features. So with that, I'll list the dissertation objectives. The first one is to describe the small scale features associated with the cross-frontal chain. So see them on the data that we've collected from two different regions. And then estimate the transport that they are associated with them and see how they impact the front. And last one is trying to describe what are the processes that are creating that mixing between those two boundaries that are associated with the small scale features. And with that, I'll like to start with my study number one. This is a study done in the Gulf Stream. So this is North America. We see the Gulf Stream again here. This is a region we'll be focusing in. This is a work done with other collaborators and other national institutes. And the work that was done for this study and the results are submitted in the last round of revisions. And this is work also that I presented probably 2 years ago in the PO seminar here in this room. So the work in the study and the data that I'm showing you here is part of a larger experiment. It's called LabMix 2012, and it stands for lateral mixing. This was done in winter, and the experiment was, this is a surface temperature satellite data. Again, we have the Gulf Stream, you have the cold water, and we have this boundary over here. You can see that at the boundary, we have high variability, and we see this detachments of warm water from the core. These ones I'm going to call them streamers. I have streamer 1, 2, 3, and 4. And the way we then study them is to deploy a Lagrangian float. So we did a survey following a Lagrangian float. This float is the way it's affected with the main flow, and it follows a volume of water of the same density. After the float, we then deployed 3 gliders following it, and also we have the resources of 2 research vessels doing cross sections. So then we have a long flow and a cross flow data. And the main objectives of this study was then to investigate how these features of surface satellite data are actually transporting heat and salt, and estimate the value of that exchange. To do this, I created a 3-degree grid. So I use all the data from all the platforms available to create this 3D image of all the drift. So first, I rotated everything to the strongest current observed with CDP. So that would be the long flow direction. And using the location of the float, so we're following this float, that float is going to be our 0 for each position. So what I'm showing in these 2 panels is a vert view of that advection of that flow. And the 0 here again is the distance from the drifter, the float, is a location. It will be a straight line, for example. And I'm showing here in the color temperature measured by our measurements. This really resembles the one in the satellite data. And the dotted here is the tracks of both vessels that are now rotated in the long flow and a cross flow. Now we can also see in salinity the structure of the streamers. We see that there's also a strong signal of them. We can see them, how they are detachment of salty water from the pore. And then the black lines is lines of same density. What we can now do with this 3D-dimensional view is we can cut a slice on it and see how the structure is in the vertical. So now this is depth, and this is the cross flow direction, right, for the flow. As the flow would have been right here. This is what we saw on the surface with the streamer here, and this is the temperature and salinity. And we see that there is interleaving between those two water masses. So we see that there's a structure in the vertical of both in temperature and salinity. And we investigate how these little features right here affect the overall structure of the front. To do this, I first decomposed all the variables. So I decomposed temperature, salinity, density, and the along and across flow velocities. Here I'm showing you an example with temperature. The first one is I decomposed them first into pro mean. So this is the entire mean for the entire survey for each location in the cross flow direction and depth. A linear trend that is telling us how the overall change of those variables was throughout the drift, and a perturbation. And interestingly, when we look at the linear trend for temperature, salinity, and density, we observed that there was an increase of temperature and salinity in the mixed layer. This was unexpected because this is a region where we have large surface flux of heat getting from the ocean to the atmosphere. And it's also not through the entire mixed layer. Another interesting thing is this increase of temperature and salinity was density compensated. So this increase, we don't see it on the density space. I'm sorry, I should say, like this black line here is the mixed layer in all the sections that I'm showing. And this increase in temperature and salinity are significantly different from zero. Here I'm showing you the same sections, but now I'm blanking out anything that's not statistically different from zero. So the natural question is now, what is creating that increase in heat and salt in the mixed layer? So for that, I do a mixed layer heat and salt budget. So this is going to be a heavy one, but we'll go step by step. So the first thing is I started with the conservation of heat and salt and mass. And I integrate these equations on the vertical. So I'm going from the zero from the surface to the mixed layer depth. And so H is going to also be varying in time. And then I substitute the decomposition that I described before. So this is an example of those variables decomposed in those three variables. And then I integrate them in time to see, to create a budget of that temperature and salinity. And sorry, pi here represents a placeholder for temperature and salinity. And A is, it's just coefficients that help me translate from temperature to heat. And what we get when we do the integration in time and vertical is this equation. And I'll go step by step. So anything that has a bar in it, it's a temporal mean. So it's the mean throughout the entire survey. Anything that has a prime on it, for example, like this one here, is a deviation from that temporal mean. Anything that has a subscript of A is a mixed layer mean. And anything that has like a hat right here, it's a deviation from the vertical mean. And here the delta are the trends that we mentioned before too. The first term of this equation is the local rate of change, so the observed change of heat and salt that we saw. The second and the B and C, so the second and third, are the mean cross and along flow advection of either temperature and salinity. Then D is that rate of transfer due to the cross flow advection, so due to that correlation between fluctuations in cross flow velocity and either temperature and salinity. And E is the entrainment, so it's how temperature and salinity is changing due to changes on the mixed layer depth and the lateral gradient of that mixed layer depth. And last, we have the surface heat and salt flux. So how is it changing due to surface fluxes? When I add all this together, we see that we didn't close the budget. So we have a budget residual. We still see an increase of heat and salt in around 5 kilometers from the flow. And so, in other words, what this equation, this budget helps us realize is first, that this increase was not due to surface flux. It was not due from entrainment to the mixed layer. And it was not done because of mean along and across flow advection. We did try to estimate the rate of transport, but we realized that the values our time series was not long enough. Values were not significantly different from 0. But the values are indicative of the lateral transfer. So I'm just showing you here the temperature and salinity, B prime, T prime, and B prime, S prime. And what this is showing is that there is a correlation between the anomalies of the cross-flow velocity and the anomalies of the temperature and salinity. And this is indicative of lateral transport. So in other words, we were not able to close the budget and explain this increase of heat and salt. But the location of that increase is related to the location of the streamers. So the summary is that we did observe a change on the front of the Gulf Stream north wall. We see an increase of heat and salt, and we were not able to close the budget. And the only possible source of that heat and salt is lateral transport. And that lateral transport is through isopignal transport. To check this, we also calculated the amount of the long isopignal diffusivity created that needed to close that budget using the residual. And then also the lateral gradient, either the temperature or salinity. And we obtained values that were close to what past studies have explained that is needed to close budgets on the cross front, in studies that actually are trying to estimate where is the formation of pitch and degree water causing, and are in the scales of the submesoscale dynamics. Another thing that we did is using those estimates of radial transports that we obtained, we also calculated a different long isopignal diffusivity. And we obtained order of magnitude similar to that of the residual. And that was really nice finding. And with this, I would like to talk to you now about my second study. This is in a different part of the world. This is Asia. So the Kuroshio current, as I mentioned before, will be in the Pacific. It will be coming this way and intensifying. This is the sea surface temperature, and we see it right here going up to the east. This is work done with, again, national collaboration with other institutes, but also international. This was work done with two Taiwanese universities. And actually in the fieldwork, I participated in this fieldwork. And I actually was in 3 of them. There were undergrads and grad students from the Taiwanese university. It was really important to be able to collect this data. And going a little bit. So I talk about the Kuroshio current going through sessions. So let me explain a little bit what I mean by Kuroshio intrusion. So this is a section of sea. The Kuroshio current will be coming this way. And as it goes north, it encounters a gap between the Luzon Strait and Taiwan. It has been observed that then this is the Kuroshio current in this diagram. It's been observed that it can intrude into the South China Sea, transporting heat and salt into this region. This intrusion is seasonal, and also it's really important, besides of the transport of heat and salt, it also affects the ecology of the region by transporting organisms from the tropical area to this South China Sea location. And what we have here is warm water surrounding Taiwan as an example of winter 2014. We can see also small scale features here at the edge of that window. And I want to give you now an example of how that intrusion looks like. So now I'm going to show you model data, model output. So what I'm going to show you here is now sea surface salinity. It's not similar to temperature, but so red will be high salinity, and blue here is low salinity. Let me see if I can find mine. There we go. And this is a 1-year run. And we're going to see, so we started in kind of winter, and we see this salty water at the north part of the South China Sea. As we started going into summer, we see that this region is like fresh, no intrusion. And that will be the Kuroshio current going up. And as we go slowly going into November and December, we see this intrusion of salty water into the South China Sea. And you can see also as it goes and comes down into Vietnam, we see a loss in salinity of that flow. I'm interested in this part here and trying to understand how that mixing across those two water masses is occurring. To do this, we did a field campaign in South China Sea, winter 2014. This is one of the cruises that I participated in, with the motivation of characterizing what is the process that makes in the Kuroshio current water in the South China Sea water. So we did, it was a month-long cruise. We did several modes of operation, and what I'm showing you here, tracks of the boat are repeated in all of them. So the gray lines is all the path that we did on the cruise throughout that whole month. And it's a project that we did collaborating with Taiwanese University, so there were students in that cruises too. And for this talk, I'm going to focus on this type of operation, and I'll give you an example of what this looks like in a little bit. But these are labeled drift wire worker 1, wire worker 2, and wire worker 3. So anytime you see this WW number, it means what drift am I talking about. So I'm going to be looking at 1 and 2. And before going into details in the instruments and how we did this, I just wanted to step back and talk a little bit about the water masses that we are talking. I keep saying a lot of a mixing between two water masses, and I just wanted to give you a background of what am I talking about. To do this, I looked into Argo floats for winter 2014, and I tried to find everything that was close to our study area. And then I said, okay, anything that's east of the Luzon Strait, I'm going to plot. So this is a salinity, temperature, and then it's a scatter plot. So anything in this region, I'm going to plot it as red in this part. And anything in this region will be now within the South China Sea. I'm plotting it here in blue. And what this graph helps me look at is that two different water masses, so two distinct curves with different characteristics of temperature and salinity. And when I'm looking at a front, or when I'm looking with this is North Pacific tropical water, which is the water that's being transported by the Kuroshio current. And it will be that characteristic water that is found in the South China Sea. And I use this to kind of say, okay, these are my limits of the two water masses, or the sources of the two water masses, and then I'm mixing in that boundary between, in the front between those two. The black line here represents the mean value of all those profiles. Okay, so how we start characterizing this? So first, I wanted to explain a little bit what the instruments that we use. So besides the shipboard instruments, so besides the instruments that we have on the cruise, which are ADCP to measure currents, the flow-through data that give us information on the surface salinity, temperature, and temperature and salinity, we use them to try to find where the front was in real time. So try to identify where do we want it to investigate. And once we find the place that we wanted to investigate, we then deploy the wire walker, which is a free float. So this one will be affecting with the flow. And then following the wire walker, and this one profiles down to 100 meters, we deploy 3 gliders. Each of these gliders had a different instrument mounted on them. So one of them, Bob, this is ours, had an aqueduct. This one was measuring shear at a 1 meter min. And then 2 from Hui had a microwriter, an instrument that helped us measure microstructures, really fine variance and temperature and shear. And we also had a 3-axis, so a towed and CTD. This one is helping us look at the large scale. So we towed this one with the boat. So and it goes to 100 meters. As you can see, all these instruments is a representation of the collaboration that we have with different institutes. This was from Scripps, the Hui, APL, Applied Physics Lab in Washington. And so if you believe me that I'm in this cruise, this is me. Trying to protect the glider, crashing against. Okay, so I talked that I'm going to be focusing on a drift. And I just want to give you an idea of what a drift looks like. So in this, it's going to be a video. The gray line is the track that we're doing with a tow CTD. So this is us in the boat towing a CTD that's profiling 100 meters. The colors is the value and salinity. I changed the palette of colors in this one. And then we have the 3 gliders that are following the wire walker. There we go. Out in this little, imagine these 3 dots are the gliders following the wire walker. So they are vecting, we're piloting them so they are in a relative position to the wire walker. We are the flow that they're having. And what we're trying to do is when we do that is really trying to show that the scales and the pattern of the front. So we see that we have salty water where the Kuroshio current is, and then we're trying to investigate all the way down as much as we can to try to look at the fresh water that's coming from the South China Sea. And then we go back. What I'm showing you here is the salinity data from each glider, and we see the variability. So we have here fresh water on top of salty water. We see interleavings of that salty and fresh water. And just to give you an idea of how far away all of them are, This is a figure of the positions of the glider throughout the entire survey relative to the wire walker. So they were like, I call this like a star arrangement following the wire walker as it affects with the flow. And each one looking at something, well, each one collected in data also. And we are going to try to focus in this type of interleaving, the salty and the fresh variability. To do this, I first want to show you what the large tails of the front looks like. So I'm gonna give you 2 examples of that long cross sections that we did with the toe CTD. So this is not glider data or the wire work data. This is the tree-axis data that are crossing the path of that array. This is for wire worker 1, so drift 1 and drift 2. The first panel is the along flow velocity though. So this is the fastest velocity that we observe in that in that section. As you can see that both of them we have a core, and it's associated with the slope of the isopycnals. The second panel is a cross flow section, then temperature, and then salinity. Temperature, and the lines here, as I mentioned before, the isopycnals. This is what I mean by the slope of the isopycnals. If you look right now at salinity, let's look at drift 2. This is a nice example of what I'm talking about with the front. We have the salty water, which is warm, salty water of the Crozier current that has a surface maximum, so that it has a peak here of salinity, and it's progressively getting fresher and getting into the South China Sea that has this fresh water on top of salty water. And if we look right at the boundary, we see these patches of fresh water, salty water, and that's what I'm interested in, seeing how those two are then layering and then mixing. We kind of see the same slope here in drift 2. We have the surface maximum, and and this one was interesting because we see a larger variability of salinity along the track. The red line here and here, that's the position of the wire walker. So this is the free-flowing wire walker that is going along the flow. And the blue lines in each one is the location of each of those gliders that is following the wire walker. Something here interesting, I like this figure, because you can see how we are sampling different regions of the front. So in this one, we are more like in the freshwater side of it, so South China Sea water. In this one, we're more in the Crozier current side. Something interesting also is like if you look at the velocity flow, these are regions that have high relative vorticity in respect to, like if we scale this with F, we'll see a Rossby number that is close to 1. So as I mentioned, I'm interested in this variability that we see here. But in this one also, we can actually, we were able to sample this one over here. So now I'm gonna switch a little bit the dimensions. This was across the flow. Now I'm gonna look at the glider data that's along the flow. What I'm showing in this slide is then salinity data for each of the gliders and wire walker in drift 1 and drift 2. So each of those different drifts and salinity. But now kind of change it a little bit. This is not depth, this is density. So when we observed the sections, we saw that density had a large variability in the depth. So it was going up and down like 30 meters on average, but it can go up to 50 meters. So to really try to analyze how much salinity is changing along surface, density surface, I plotted in density. So this is the same density. And this is just time in days of the survey. So what we see here, for example, in drift 1, is that along the same isopycnal, we see a high variability of salinity. If we use glider heel as an example in drift 2, we can observe the surface maximum that I was talking about before. So it has a constant salinity along the same isopycnal, and it's a nice example of what the water that is closely related to the Crozier current looks like. In this drift 1, you can see that there is this signature of the surface maximum of salinity, but it then has interleaving between them. And that's what I'm interested in, seeing that interlayering of those two patterns. As a reminder, the distance between each of these gliders is roughly around 4 to 6 kilometers. So now that I've shown you the data of the gliders and the tree-axis, I wanted to show you a little bit, well, where are we sampling in those two endpoints that I mentioned before. So between the Crozier current water and the South China Sea water, where are the samples that we collected? Again, drift 1 and drift 2. The black lines are the mean values from the ARCA data. So this will be the mean profile of the solution is in water, and this will be the mean value of the current being transported by the corrosion current. The color is a percentage of bins that have that characteristic of temperature salinity. So here, yellow colors mean that we sample mostly water that was in between those two, that have characteristics between those two water masses. And here, yellow, so it shows that we sampled water that was mostly influenced by the corrosion current. So we mostly sampled water that was closely related to the corrosion current. The color lines is the median value of temperature and salinity for each of the glider and wire walker at a different density place. And what's really interesting of this is you can see the large variability, so the fluctuation of that profile, which means that you're sampling fresh water and then in the density lower than that, you're sampling salty water and you're having large variability. And that's the interleavings that we're seeing that are coming from the different water masses. And the TS-based science will be seeing that. As we see the drift one, wire walker one, has larger variability like this one, all the data that I'm showing after this one is only coming from just drift one, wire walker one. So the next step for me is to try to understand what is creating the mixing. How is this two water masses mixing? And for this, I use two tools. The first tool that I look at is density ratio. So density in seawater is driven by two factors, temperature and salinity. But they affect density differently. High temperature will give you low density, and high salinity will give you high density. So just to give you an example, and density ratio is evaluating the stability depending on temperature and salinity. So it's looking at the vertical gradient of temperature and looking at the variable gradient of salinity and doing a ratio of that. And just to give you an example of what type of structure, so what kind of dynamics can happen when density is, because of this characteristic of density, imagine if you have salty, warm water on top of fresh, cold water. So temperature-wise, you're stable. You have warm water on top of cold. But salinity-wise, you have salt water, so saltier water with fresh water. And so the closer this ratio gets to 1 and something like that, the more you can get to instability, where salinity can then drive the density. And also important is temperature and salinity have a different viscosity in diffusion. So they are mixing in the molecular ways differently. This creates instability that's called double diffusion. In the example that I just gave you, it's called salt finger because you have salt on top and you kind of start having salinity going down. And you can identify with density ratio between 1 and 4. The other example, so the reverse of that would be to have cold, fresh water on top of then warm and salty water. So now salinity is stable because you have fresh and salty, but then temperature, you now have cold over warm. So that's called diffusive convection, and it's now in the other, I call it like the other flavor of double diffusion. It is between 1 and 0.25. But an easier way to see this with the Turner angle, which is the same, it uses the same parameters as density ratio, but it gives you a finite number. So the only options are between minus 90 to 90 degrees. And I use this parameter to identify in our profiles where can double diffusion be important. And I use a stricter definition of what the double diffusion can cause instability. So between 75 and 90, which is a density ratio of 1 and 2. And for diffusive convection, minus 70, less than minus 75. So it will be between 1 and 0.5. The second tool that I use is shear. So as I mentioned before, we have two instruments that can measure shear. And we use this to then describe how the interleavings are unstable to shear. So we look at the Richardson number, and Richardson number is certification n squared over vertical shear. And this is the way we obtain shear. So it's a vertical gradient of the velocity that we observe. And what we do is investigate if these profiles are potentially unstable to shear, looking at when this value gets lower than 1/4. In other words, we define this as reduced shear. So any moment when this value is positive, so at any moment that shear square is greater than 4 times n squared, we're calling that this is potentially unstable to shear. And I'll give you a little example of how this looks in real life. So this is one profile, so this is still depth, but now I'm just showing you the value of a parameter, right? So this is the continuous black line is salinity, and the dotted line is temperature. So this is a mixed layer. So let's focus in minus 80 below. If you look at this, this is a salty layer on top of a fresh layer. And this is fresh layer here is the interleaving that we're seeing of fresh water. And this here is temperature that's stable. You have warm water, and then you get colder and colder. So if I show you the values of Turner angle, and I'm plotting here this line, is that range of when it starts being unstable to double diffusion, either by south finger or by the other one that's diffusive convective. And we see this part being unstable, potentially unstable to double diffusion. So we see this range of values in that Turner angle that is higher than 75. That corresponds when we see the intrusion, right? And now in this one, the continuous line is 4 times n squared, and the dotted line is n squared. So in other words, I'm doing this, right? So I'm just showing you this one, and I'm showing you this one. And any moment when that's positive, we're saying that's potentially unstable to shear. So I'm just giving you like, they're saying, okay, these regions can have this type of instabilities, or potentially can have this types of instabilities. And it corresponds to this interleaving, this cold kind of interleaving that we see in salinity. So I did this for all of the profiles and all the sections that we have. And I'm going to show you an example of a continuous interleaving that we see using the wire walker instrument. Because the wire walker was a lucky one, it had shear and it had dissipation measurements. So we were able to compare those two in that instrument. So this is depth. Now this is time in hours, so it's roughly less than half a day. And each line is a salinity profile. So similar to what I showed you before, but now many of them. And what we have here, so you can see that the fresh water here intruding into it. And the red dots are anything that's Turner angle higher than 75, so unstable to south finger. And anything that is potentially unstable to shear is in blue dots. So we see this pattern of the instability on the upper layer, edge of that interleaving, and also then shear. The new instrument that I'm adding here, the new measurement, is dissipation of thermal variance that we have in the wire walker, so pi. And anything that has a value greater than 10 to the minus 6, I'm plotting it as a black cross. So we also see this relationship of where the interleaving is, and when we see patches of high dissipation. We also see patches as below that are intermittent. So another question that arises from here is, how is this affecting our characteristics? How is this mixing both our layers? So I just give you an example of one of those interleavings. I'm using this one, which is the same profile. And I'm also using, just to show you how we can integrate the other instruments, I'll show you a profile at the same time of the glider 1 and glider 2. Remember that glider 1, is Hilo. This will be Bob. Hilo had epsilon, so dissipation of kinetic energy. And then, so we have this really interesting pattern in TS space where we have salty water, so this is salinity, right, and temperature. We have salty water, and then fresh water and salty water. And you can see how the Turner angle, so the double diffusion stability, is right there in the edge between those two water masses. And associated with this, you have high dissipation values, a positive reduced shear value, and also a positive pi. And this is right in the mix in between those two edges of a interleaving. So the next natural step for me here was to then try to associate where do we see dissipation, or how dissipation is occurring using those two reduced shear and Turner angle as a way of classifying the data. So what I look now is I did like subsets. So I take samples that first are only unstable to shear, then samples that are only unstable to double diffusion. So this is with the south finger. This will be when shear is important. Sections where both are simultaneously unstable to both shear and double diffusion. And then sections that are doubly stable, so that means both temperature and salinity are stable, so there's no instability of double diffusion. And there's no shear, so n squared is greater than s squared. And what I do here is then I parameterize the thermal diffusivity value, KT. We're using the chi from those measurements from the wire walker. And we observed that, as expected, the lower diffusivity value is from the profiles that are stable in both shear and double diffusion. We see that profiles that were only unstable to double diffusion had a higher KT than shear. But surprising or interestingly enough, profiles that have both the double diffusion and shear has the highest diffusivity values. I really like this pattern because it shows how important it is to kind of observe and identify what process is driving the vertical mixing. So as I mentioned before, two of the gliders had epsilon, so the dissipation of kinetic energy. And what I do is I do a parameterization then of K rho using this formula from Osborne 1980s. The interesting part of this formula is that you need to choose this coefficient, the mixing efficiency. Past studies of only shear regimes, or when only shear is important, or they only see shear, use 0.2. But a lot of other studies, like St. Laurent and Smith, for example, they do a lot of compare of microstructure data and density ratio data to look at what would be correct to use in regimens where it has also double diffusion. And when we see, and they observe that mixing rate efficiency is close to 0.8, and this can vary depending on the density ratio, is more accurate than 0.2. So then I estimate this value for profiles that are completely stable to everything, and because we observe it's a low value. And then I calculate it for profiles that are potentially unstable to both. Sorry, both to cell fingers. And then I estimated using a 0.2 and a 0.8 to see the difference of that will be less. It was a little bit close to an order of magnitude difference. Lastly, what I then do is say, okay, I'll use density ratio to parameterize the value of KT, of my vertical thermal diffusivity. And I did this using a parameterization of Racco and Smith, who later was used by Nagai in the also the Kuroshio current extension, which is north and east of where we were. Yeah, east, sorry. So here we have the parameterization values. And this is the actual KT observed that we obtained, that we did from Kai, so from the past measurements that I mentioned before. We see that overall, the parameterization underestimates the value of KT, but what I did here, then I use my subset again of identifying what profiles are stable to double diffusion, what profiles are stable to shear, and which ones are stable to both. Interesting, we see, so the black line is unstable. Unstable to double diffusion, all including including shear and non-shear, and the red line is potentially unstable to both. They follow the same slope; they're still higher, but they follow a similar slope. But interesting, profiles that were only unstable to double diffusion were high and had a different slope. So the parameterization was not correct for these profiles. It was interesting because these ones are completely just unstable to double diffusion. So being able to differentiate between when a profile is unstable to shear and to double diffusion gave us a different different parameterization and different relationship with the parameterized KT. And this actually describes the importance of being able to identify when double diffusion is the only one being important in the profile. To finalize this, I estimated the vertical heat flux using this equation. So I'm trying here to understand how much heat is actually being lost by these interleavings with the parameterized KT. And I did it for each of the subsets to show you what will be the difference between classifying this process as different. And you can get the difference up to 40 watts per meter square, or even higher than that. If looking at, and as we talked before, the highest one was when the profile was stable to both double diffusion and shear. So in summary, we observed interleaving values that were associated with dissipation in the boundary between the Kuroshio current and the South China Sea. These interleaving were both potentially unstable to salt fingers and shear instabilities. We were able to classify when one was the only one present and when they were both together present, and observe that the higher thermal variance dissipation was when both double diffusion and shear were present in the profile. And in the summary and conclusion of our studies, and using our objectives as a base of what we find, we see that we did see a change in the front. We saw an increase of temperature and salinity on the Gulf Stream North Wall in the presence of submersible features. We saw that we were able to estimate a horizontal and also a vertical diffusivity values that were one from direct measurements and the other one from our budget that were consistent with past studies of frontal exchange. And lastly, it's really important to be able to identify what process is happening between those small scale features, how this is mixing, to correctly parameterize those values of mixing. So before I end, I just want to acknowledge and say thanks to my committee members. They have always been supportive and have an open door relationship with me, and just not just academically, but professionally, that helped me make decisions and be certain of what I'm doing. Also, many thanks to the OSU LIDAR group. That was the first ones that I started going in to see here in the United States, and it was really fun. All of them who passed. Some of them are students who were here in the past and now they're around the world. It's never a dull moment with the OSU LIDAR group. It's actually Pat. We're calibrating a glider in the middle of apparently woods, but this is Corvallis, another. That was fun. Special thanks to my advisor, Dr. Keith Sherman. This is one of our cruises. I really like sailing with you. I could not be here if it wasn't with his help and his guidance, his patience. He definitely made me seem in the eyes of a scientist that was really hard for me, and he really pushed that to see myself that way and talk that way and represent the science that I'm proud of doing. Also, I just want to keep a small acknowledgement to my college, Facultad de Ciencias Marinas, which I also would not be here if I haven't not gone to that university and get the constant reassurance of the professors there that I can make it here and I can do a good job. Thank you. Many thanks to the entire CS community. As I say, it's an honor to be here presenting to you this work. The PO graduate students who hear me talk about this, postdocs who've been just so supportive and a mentor to me. Lori Hartline and Robert Allen, you make this flow. Thank you so much. Special thanks to the PLC community, Melissa McCracken and Melba, which we started this. Jen, T, Chris, Adrienne, and Elisa, thank you so much for just being Bill and support. Special thanks to Jane White, Tuba, Flaxen, Nachi, and Joseph Orozco to giving me voice and naming some of the worries or some of the barriers that I put myself and that I see in this community and has helped me overcome them. Lastly, Corvallis, I will put a picture of everybody here if I could. And if you have like a week, I will do it and explain to everybody how it was so important to meet you, how much it helped me in everything I did. So special thanks. This is also like a part of my work is your work. My roommates who were my family here took care of me, make me feel so loved. The Latin American community, Alas, you gave me the cultural backbone to also get through this. Thank you so much. You know who you are. I love you all. And let's give you a second to digest the pictures. Some of them have a lot of years on them. Don't look that too close to those ones. Lastly, my family, Tijuana and Ensenada family. Thank you so much. This is my entire, like my parents and my brothers. I wouldn't be here if they weren't for there. And they cost some love. Thank you. This is just a thank you to this mountain that I haven't been able to climb. And it's like, I will climb it someday. I swear I will. And questions.
Okay, we have time for questions.
Yeah.
So in your histograms where you're showing the high mixing or the high dissipation rates in the boat scenario, you presented me as it's really not a normal distribution. What do you make of the bi-normal character of that?
That's a good.
Focus on the minimum as opposed to the
Yeah, thank you for that. So for example, in this one, right? So I usually I use the median value for that one. So I was careful to really talk about the distribution, but as you see, the data points in this one was not as much as the other ones. So it could also be that we just didn't have the enough. This is just sorry, I forgot how many days. 3 point, less than, it's around 3 days of data. So I'm cautious in saying like that this have to be bimodal distribution because it could just be that if you got enough samples, it could be not bimodal. But it's important to mention that in other studies of double diffusion and shear in different regions, like Southern Ocean, they do see a bimodal distribution and profiles are unstable to both shear and double diffusion. And I think it's just a little bit of relationship of how it might be affected by the, depending of the shear, depending of the stratification, one could be leading the dissipation compared to the other one. So we do see that interaction when both of them are present. Those are the questions.
Great presentation. Do you expect these results to change with the changing low temperatures?
Oh, that's a really good question. So yes, so as I mentioned before, I'm going to use actually this one. So as I mentioned before, for example, for the Crozier current, the intrusion, for example, is really dependent of the transport that is coming from the Crozier current and how much is going in, for example. Also, like if we picture stuff like this, a Gulf Stream also, that transport of that water also depends a lot of that entire subtropical gyre. The subtropical gyre by itself is also dependent of, it's wind driven, so it depends on the circulation of the wind. Changes in the pattern of that wind, which is related with changes of temperature globally, can then reduce or amplify the transport of volume of water. So that will definitely affect the way either the Crozier currents, the amount of times the Crozier currents intruding into the South Sea, or the amount of heat that is being transported by these currents. And then one of the objectives of one of the motivations of this kind of study is if we understand right now what's happening and how it's affecting, we can then go back and see, okay, if this is how much the transport is going to change, we can have the correct parameterization to observe how much the heat exchange and the salt exchange and the momentum exchange will then vary. So in other words, both of them are embedded in the larger dynamics of the ocean, so that definitely will be affected by changes in the ocean patterns that are affected by the climate change.
Great. Any other questions? Oh,
Yeah, just follow that. So,
Yeah.
so in the simulation, we saw a chunk of warm water going to South Tennessee.
Yeah.
And then it goes away.
Yes.
So can you like make an estimate based on what you learned about the heat fluxes to say how long it would take to go away?
Yes, and I can't do it right now. But yes, if we, for example, if we estimated the amount of water that came here for like the time that we can see that in the model, we can then kind of estimate how many times we saw interleaving and then multiply that by the heat exchange or the salt exchange. We can obtain a salinity BTCD value using the density ratio too. And then we can estimate the amount of mixing occurring and how fast this will then completely dissipate. Even if, for example, when was started and when did we cut it off, for example, we can then see how long it would take to dissipate inside the South Sea. Sorry, yeah, good question. Oh,
We'll do that later.
okay.
I think Melanie had a question.
Yes.
Oh, that's a really nice talk with you. It's very interesting work. So you were talking about how these mechanisms carry out mixing across the front, but some of the sub-mesoscale literature that, not exactly the papers we're referencing, but as you know, talks about the formation of these sub-mesoscale instabilities, let's say after a wind-driven mixing event, as a mechanism for re-stratifying the mixed layer. And I just wondered if you saw any evidence of those kind of events in your data.
Yes, so there was a study done in exactly, let me go back to this one. There was a study done in this data set, Steve Thomas et al., that looked at this portion of the drift when they saw a strong wind event. And so that wind event was along the front, so down front of that, the Gulf Stream. And they observed evidence of then negative potential vorticity, which is the signature of symmetric instability. And they saw higher mixing rates higher dissipation rates that they can account for just the wind forcing. And so they account that to the symmetrical instability that's doing that restratification faster. So I didn't do that directly to the data, but that it was observed in this one in the Gulf Stream exactly. And as you mentioned, is because of that mesoscale stability, what they call symmetric constellation.
All right, let's thank Ollie again and.
All right, we'll take a short break and then the committee can come back.